So I want to talk about proper morphism. So which is generalization of finite morphism. So in particular, finite morphisms are examples of proper morphism. But to do proper morphism, I need fiber product to define fiber product and immersions, closed immersion, open immersion. So what I am planning to do in today's lecture, I will talk about two things. One is this closed immersion and open immersion. You can mix both, and what is called locally closed immersion. So locally closed subset is intersection, you can think as union of intersection of closed subset and open subset. So if you know what is called locally closed immersion, then you know in particular what is closed immersion and what is open immersion. Is it clear what I am saying? So locally closed subsets are more general object than closed and open. So it's a intersection with closed subset with an open subset. No, I mean, okay, I'll explain. So locally closed immersion. Or embedding. In algebraic geometry, embedding and immersion are kind of same. So let's talk about immersion. I'm not talking about tangent spaces and all. So let's talk about immersion. Let's write immersion. Sometimes they are called also embedding. So what is it? So for a pre, I will do it for pre. So suppose OX is a pre variety. So that means what? That means X is some, you have some open cover UI. OX is a sheaf of K algebra. And if you restrict OX to UI, then it becomes isomorphic to OUI as K algebra isomorphism, right? So, and you know that what is morphism between pre-varieties. So, if X and Y are two pre-varieties, so your morphism is roughly, it is a continuous map from X to Y, which sends takes the regular functions on U to regular function on F inverse U, right. So, this is what you call the morphism of pre-varieties. Okay. Now, I want to talk about locally closed subvarieties. So, okay. So, before doing that, let me put some facts, or I leave it as exercise for you, for your assignment problem. So, so if X is a XOX pre-variety, then implies X is Noetherian as a topological space. Second is that if it is a pre-variety, then OX is a subsheaf of CX, where CX is nothing but sheaf of continuous functions. OX is sheaf of K algebra, and C is a sheaf of continuous functions on X to K. So, if you take a global section, so if F is in a OX of X, then you can talk about the open set U, set of all point X belongs to X as the F of X is not equal to 0. Then this, then if you consider 1 by F, so 1 by F is as a function, is it as a map, it is defined on U. So 1 by F belongs to OXU. Very much like affine variety. But all these things are true. I am not going to, I leave it as exercise, because these conditions will be used somewhere at some place. And the most important thing is that the pre-varieties, you can write it as union of affine open cover, and the affine open subsets forms a. So, what is a affine open subset of X? That means any subset of X which is isomorphic to some affine variety. So, affine open subsets forms a basis of X. So, this is the most important thing, that any open subset you can find a affine open subset which is inside that open subset. So, when you are doing a local study of pre-varieties, so basically you are working with affine varieties. Okay. So, now what I want to talk about, what are called locally closed subsets of pre-varieties. See, I don't want to go into proof of all these things because it will take some time, but I just leave it as exercise. You can do on your own. It's not difficult, but you have to do many checking. So, I leave it to you to check these things. Locally closed subsets of a pre-variety. So, what is if X is a topological space and I say that Z is a locally closed subset, what do I mean? That means Z is union of finite union, say, over I equal to 1 to n, where Ui is open in X and Ci's are closed in X. So, this is what is called, for a topology, what is called locally closed subset. Now, the point is that if I start with if I have a locally closed subset, I can talk about a variety structure on Z induced from X. As you know, just subset is not going to give a variety. A variety structure is something special. So, I am saying, what if I have a locally closed subset, it induces a variety structure on Z. X, the variety structure on pre-variety structure on X, sorry, I should say pre-variety structure on X induces a pre-variety structure on Z, and then it's called sub pre-variety of X. Z is called sub pre-variety. So, how so to give a pre-variety structure, I have to explain what is the sheaf. So, OZ, so Z as a topology, so this is a subset, so it has it is a topological space. Now, what I want to explain, what is the sheaf OZ. So, OZ of what? OZ of some U, where U is an open subset. U is an open subset, then OZ of U, these are set of all functions U to K such that for any X belongs to U, there exists a Vx which is a sub open in X and containing X, such that and an element in G of Ox or of Vx, such that Vx intersection Z is in Ux and the function f restricted to Vx intersection Z is equal to G. G restricted to Vx. So, what does it mean? That means you consider all the functions from U to K, locally it should look like a restriction of a function on X. See, if you consider all the K valued form map from U to K, such that locally for every X belongs to U, you have an open subset in X. So, and such that which contains X and a regular function and a function, this sometimes I call it a regular map because already it is a pre-variety. A regular function G such that when you restrict to this Vx intersection Z, it becomes it is equal to F. So locally it is given by, it is coming from regular function. Now claim is that this is a sheaf. OZ is a sheaf. And this also sheaf of K algebra. So but not this is sheaf of sub algebra. It may not be sub algebra. OZ of U, you may sometime you may not be. It is not OA sub of OX of U, but this is a sheaf of K algebra. What is sheaf of K algebra? Even when Z is closed. So if it even if it is not always, it's a sheaf sub algebra because of you will see that when Z is a point, you just check for Z is a point. When Z is a point, then you will see that this becomes a different. Which is a subsheaf? No, it's not a subsheaf. When Z is a locally closed subset, but when U is sub of this open subset of X, then if you restrict OX, first of all, this is not a, see, this is, first of all, this does not make sense, because if I am taking only U, which is a subset of Z, this is on sheaf of Z. So at most what you can ask, whether OX restricted to Z and OZ. First of all, if you take a Z is a locally closed subset, does it make sense? If Z is a closed subset, for example, OX restrict to a point is not a, that does not have a sheaf property. So this is the best way of, so you have a stock, definitely have stock at a point. So OZ and OX, so but the point is that if U is open, then OX restricted to U is isomorphic to OE under this definition. For any pre-variety, if U is open. But the important point is that with this, if Z is a closed, locally closed subset of X, then ZOZ is a pre-variety. Closed? Yeah, you will see, I am saying you take Z is a point. So now you define what is a subvariety. So definition, a locally closed subset so locally closed, or I will write open, closed, subvariety of locally open and locally closed. Locally open is always open. The open subsets are, these are called intersection of closed and open. So this need not be open, neither closed. So that's why it's called local. So what did you write that open or closed? Back, I'll complete, then you see. Subvariety of a pre-variety XOX is a pre-variety ZOZ where Z is a locally closed subset. And OZ, you get it, OZ is as above. So here what I did, I took a locally closed subset, then I constructed a sheaf. All right, I constructed a sheaf. So now I say the locally closed subvariety of X is of this form. That means you just construct that means it's a locally closed subset, and the sheaf structure is induced from OX, right? From OX only you got the sheaf structure on Z. You define the sheaf on OZ from X. So these are called locally closed subvariety. Now, if Z is open, then you call it open subvariety. If Z is closed, then it is called closed subvariety. Okay. So for a pre-variety, you say if it is basically an open subset in X, and the sheaf structure is induced from the pre-variety. Similarly for the closed subset, and similarly for locally closed. So you take a locally closed subset and it induces a sheaf, and that is basically a subvariety, locally closed subvariety. No, it is not. For example, you just take some surface and you take a curve which is one dimensional, and now you intersect with some open subset. So now this portion is a locally closed subset, but this is not a closed subset. Okay, so now following definition, a locally closed immersion is a morphism of pre-varieties such that so what does it mean? That means in some sense that you take the image, that image is a locally closed subset. So it has to be injective because this is isomorphism. This Z is, you can think as an image of Fx. So Fx is sitting inside Y, but this image is a locally closed subset. So then you call it a locally closed immersion. And now you say it is a open immersion if Z is open. You say it is a closed immersion if Z is closed. Right? Because it is isomorphism and Z is an inclusion. So it has to be injective. Yeah, this is inclusion. I is inclusion. So in other words, X is isomorphic with with a locally closed subset. The image is a locally closed subset, basically. Then it's a closed immersion. Then you call it is a closed immersion. The map F of X to Y is a closed immersion. If it is an open subset, you call it an open immersion. If it is a locally closed subset, so point is that locally closed subset you can give a canonical subvariety structure, sub-pre-variety structure, not just closed or open. This is more general. Right. So proposition. So now so what is the criteria of a morphism to be closed closed immersion? So criteria. So let f x to y be a morphism, then following are equivalent. F is a closed immersion. See, what is the natural example of closed immersion? for affine variety. Any closed subvariety is a closed image. It is an example of a closed. So that means at the ring level, there you have a surjective map. The coordinate ring of A and coordinate ring A mod A, right? So ring level, it is a surjective map. Exactly same thing you will see here. F is a closed immersion for any U Y open affine. So this is a morphism of pre-varieties, okay. So if I don't say anything, then you assume that everything is a pre-variety. Open affine, the F inverse U is affine, and the map from OY of U to OX of F inverse U, this is a map of this surjective. This is now I said now in the previous class I said that whenever you work with pre-variety or more general objects like this, so once you do it, definition is for every affine open, and then you say that if there is one cover for such, if it happens, then it is true. They are equivalent, exactly same as. So there exists. So this is basic. This is due to the fact what I said just before, that these affine open subsets, they form a base for the topology. So everything you can. So whenever you intersect two open subsets, I can find a affine open which is sitting inside that intersection of two opens. So that gives you this independence, that if you do it for one, then if you take another cover, for that also it is true. So that's the point. That's that there exists an affine cover X union of Ui such that O X of F inverse such that F inverse Ui is affine, and Ox of F inverse of Ui Ox this way map Ox of Ui. This map is surjective. Double arrow means surjective, right? So this is this is not very so this is criteria of a closed immersion. So this is if you take a open subset inverse image, so for closed immersion, there first of all there are affine maps. That means if you take a affine open subset in downstairs, the inverse image has to be affine, and not only that, it is a surjective map at the shear so this is criteria of closed immersion. Right. Now you see that sheaf, for example, A to A. Huh? Oh, sorry, this will be Y. Sorry. Thank you. Because I am talking about F inverse. Now you see that A and A mod A. Huh? This is OY. Yeah, you see here A and A mod A. Now this sheaf is OZ is basically A mod A. I mean the A mod A tilde or right. The sheaf is different from the sheaf A. So you really cannot say it is a subsheaf. Even in the affine case. Right? So in the case of point, it will be A mod M. Anyway, so okay, so now what I am going to talk about is Yeah, proof I leave it as exercise. I'll discuss whatever I'll leave it as exercise, and I'll discuss in some tutorial session. I'll do some tutorial session, 2 or 3 problem session I will do, and that time you will see that proof of most of these facts. Whatever I am leaving out, I'll do it, because it is becoming, then explaining will be easier. Otherwise, if I start explaining, then I cannot do the remaining thing, the main part. But I leave it as exercise. We'll discuss in tutorial session.